The force method can be a very efficient way to analyze indeterminate frames if they only have 1 or 2 degrees of indeterminacy. So in this problem we're going to analyze an indeterminate frame using the force method of analysis. The key concepts we'll use are calculating the degree of indeterminacy, selecting a redundant for the force method of analysis, and predicting deflection of a frame using virtual work. And here's our frame. There is a fixed support at A and a rocker at C. We want to find the reactions at both of those points. The moment of inertia is given for each of the members of the frame, and the modulus elasticity is that of steel. And here's our approach. I always want to start by approximating the answer. Because after performing lengthy calculations using the force method, we want to have something to use to ensure that we have a reasonable answer. And so we'll have that approximate answer to compare against. Then we're going to look at the degree of indeterminacy so that we know how many redundants there are. We'll choose the redundants and we'll write the appropriate equations of compatibility. We'll then calculate deflection of the primary structure which is another way to call the released structure the structure that does not have the redundant anymore acting anymore, and deflection of the primary structure due to the applied loads. Then we'll calculate or predict deflection of the primary structure due to a unit redundant. So we'll pull off the applied loads and just apply a unit redundant. We'll then put those into our equation of compatibility and find the redundant. With that, we can use our equations of equilibrium to find the remaining reactions. Then let's evaluate the reasonableness of our answer by comparing it with the approximation. Great, let's get started. Step 1. Let's approximate the answer. To do that, let's look first at the vertical support reactions. So we have our frame with a vertical support at CY and AY, uniform distributed load across the top segment at 8 kilonewtons per meter. And let's assume that the load is carried by the closest vertical support. That means we'll take half the distance, so 4.5 meters will travel to AY, and 4.5 meters will come to CY. So AY is approximately 8 kilonewtons per meter times 4.5 meters, 36 kilonewtons acting up. CY is approximately 8 kilonewtons per meter, 4.5 meters, 36 kilonewtons acting up. Now the moment support reaction. That we have at A. For this, let's ignore the effect of the 2 kilonewton concentrated force. It's a pretty small magnitude force compared to the total downward force of 36 times 2, 72 kilonewtons applied vertically. And so let's just idealize our frame as fixed at one end, roller support at the other end, with a uniform distributed load and a 9-meter length. We know we have a moment reaction at A. Now, although we haven't yet introduced it in the text, if you look inside the back cover, there are many different loading conditions for frame elements that are supported fixed or fixed roller, like we have. So if we look inside the back cover at this situation, we see that for a beam fixed at one end, roller at the other, uniformly loaded, the moment reaction is omega L squared over 8. So let's use that to approximate our moment here. So MA will be approximately, and remember it was drawn in the other direction in the back cover of our text, so it'll be minus omega L squared over 8. So you have a minus 8 kilonewtons per meter, 9 meters long. We'll square that term, divided by 8. We have a minus 81 kilonewton meters if we assume that it was clockwise. So once we finish applying the force method to determine the reactions, we'll come back and compare against these predictions. Now step 2. Once we figure out how many degrees in determinant, we'll select our redundants and write our equations of compatibility. So let's start with indeterminacy. Well, we have a vertical reaction at A, a horizontal reaction at A, a moment reaction at A, and a vertical reaction at the rocker, which means we have 4 unknowns. From that we subtract the number of free bodies, 1, 3 equations of equilibrium for that free body, and we get 1 degree indeterminate, which means we need to choose one redundant. We can choose any support reaction or any internal force as long as the primary structure, the structure released from that redundant, is still stable. In this case, I'm going to choose the vertical reaction at C. So let's come down here and draw our primary structure subjected to the applied uniform distributed load, and it will have a deflected shape that looks something like that. Oops, can't forget, there's the horizontal concentrated force also acting, which means my deformed shape probably has a little more curvature. There we go. This distance we'll call delta C. It's the change in vertical position between the end of the primary structure under the applied loads and the end of the primary structure after it deforms. Then we'll superimpose that with our same primary structure, and we'll take reaction CY and multiply it times the effect of a unit force applied vertically at C, our unit redundant. This will give me a different deflected shape. Looks something like this. And the change in vertical position of point C we'll call our flexibility coefficient F subscript CC. So my equation of compatibility becomes the vertical deflection of the primary structure subjected to the applied loads plus CY amplifying the deflection of the structure, the primary structure, due to the unit redundant, have to balance out or add up to 0, its original position. Now we're ready for step 3. We need to calculate deflection of the primary structure. So the frame shown without the vertical reaction at C, and that deflection due to the applied loads, the uniform distributed load and the concentrated load. Since this is a frame, we're going to use virtual work. Double integration, moment area, conjugate beam, none of those would work very well for a frame. I'm going to start by finding the moment equations due to the virtual force first. Now we're going to need to divide our frame into 3 segments. We have our unit redundant, not our unit redundant, our virtual force applied at point C, and we'll have one equation for moment. We'll call it x1. We'll start at point C, and it will continue up and 3 meters to where the concentrated force was applied. Then we'll need a new equation. We'll call it starting at x2. And if we look from this side, we'll need a new equation from B to A, and we'll call that x3. And so let's start with a free body diagram of the frame cut in the range of x1, and let's keep the bottom piece. So it is x1 long. We have our virtual force applied. We have our unknown shear, which is a function of x1. We have our unknown virtual moment, which is a function of x1. Let's apply moment equilibrium. We'll sum moments at the cut, and I could choose either direction to be positive for this summation. I'm going to choose clockwise since that's the direction that my little m is drawn. And the only thing that contributes moment about the cut is little m, so my moment equation all along x1 is 0. Well, that'll be very helpful. That makes my calculations in the virtual work method much easier. Now let's cut it within the range of x2. I'll draw it, and now it is 3 meters here, and then x2 a little bit farther. We have our virtual load applied, our unknown shear as a function of x2, our unknown virtual moment as a function of x2. Let's sum moments about the cut again. I will choose clockwise as positive again. And the only contributor is the virtual moment as a function of x2. So that equation also is 0. Next, let's cut it in the range of x3 and draw a new free body. So I draw a free body diagram of the section cut in the range of x3, and I'll keep the right piece. It is 6 meters tall, x3 long. We have our virtual load applied here, our unknown shear as a function of x3, and our unknown moment as a function of x3. We'll sum moments about the cut. Again, we'll take clockwise as positive. We get the moment at the cut, and our virtual force acting through a distance of x3. So my equation for moment in the range of x3 is minus x3. Now that we have all of our moment equations due to the virtual load, let's get our moment equations due to the real loads. The uniform distributed load and the concentrated load. Now let's point out and save a little bit of trouble here. I don't need the moment equation in the range of x1 or the moment equation in the range of x2, since the virtual moments are both 0 in that range. When I take these, multiply them times those, we're integrating 0 in a definite integral, and we'll get 0 contribution. So I need only consider a free body diagram cut in the range of x3, much like we did before. 3 meters, 3 meters, x3 long. We have our concentrated force of 2 kilonewtons, our uniform distributed load of 8 kilonewtons per meter, our unknown shear as a function of x3, and our unknown moment as a function of x3. We'll sum moments about the cut, and we'll again take clockwise as positive. We have the unknown moment at the cut. We have a positive contribution from the uniform distributed load acting over a distance x3 gives me the total force. Its resultant location is x3 over 2. We also have a positive contribution from the concentrated force acting through a distance of 3 meters. Put those together. In the real moment, in the primary structure or released structure, mx3 is a minus 4 kilonewtons per meter, x3 squared minus 6 kilonewton meters. And a reminder, our primary structure has no rocker support at C. Now we're ready to combine these in the virtual work method of deflection prediction, and we'll get delta C, the vertical displacement of the primary structure at C. So let's calculate delta C, which will be the vertical displacement of this frame without a rocker support, but with the uniform distributed load and the concentrated force. So to calculate that using virtual work, we'll sum integral from 0 to L virtual moment times real moment over EI dx. So in the case of this structure, we said that the component here in x1 and the component in x2 each are 0, so we only need to integrate from 0 to 9 meters. Little m, which we found was a minus x3, and big M, which we see here, minus x3 times minus 4 kilonewton per meter, x3 squared minus 6 kilonewton meter, dx3, all divided by E, I, and this is the moment of inertia specifically for member AB. Let's consolidate those two terms. We'll have negatives cancel, 4 kilonewton per meter x3 cubed plus 6 kilonewton meter x3. All of that integrated with respect to x3 over E I for member AB. When I integrate those, this term raises to the 4th power, and then we divide by 4, so I'll get 1 kilonewton per meter x3 to the 4th. This term raises to the squared power, divide by 2, plus 3 kilonewton meter x3 squared, all divided by EI for member AB, integrated from 0, or evaluated now, at 0 and 9 meters. So I get a 1 kilonewton per meter, 9 meters to the 4th, plus 3 kilonewton meter, 9 meters squared, all over EI for member AB, minus 0 at the other limit. If I now evaluate this, I get 6,804 kilonewton meters cubed, and our modulus elasticity, 200 gigapascals, can be rewritten as 200 times 10 to the 6th kilonewtons per meter squared. Our our moment of inertia for member AB is 1,250 times 10 to the 6th millimeters to the 4th. All of that in the denominator. We see that we have this meters squared in the denominator, which comes up here, so we have meters to the 5th over millimeters to the 4th. So let's convert the numerator. There are 1,000 millimeters per meter, and we have that unit to the 5th. Put all these together, I get a positive 27.2 millimeters, and we applied our virtual force down, so that means that my displacement is down. Now we're ready for step 4. We basically get to do it all over again, because we're going to predict deflection of the primary structure which, remember, means there is no rocker support at C, and we want that deflection due to the unit redundant. So we'll take off the concentrated force and the uniform distributed load, and we'll apply the unit redundant, which will give us a deflected shape that looks something like that. And we said this will be our vertical deflection. It'll be the flexibility coefficient FCC. But notice that my real structure, because we're going to need to use virtual work, since it's a frame, but my real load looks just like my virtual load. So my calculation for virtual work becomes the integral from 0 to L of little m squared. And remember, little m in the range of x1 and little m in the range of x2 were both 0. So again, it's only in the range of x3, so we integrate from 0 to 9 meters. Little m we had found was minus x3, so we'll take that minus x3, square it, integrate, or divide by E I for member AB, and integrate with respect to x3. which means we take this term becomes x3 squared, we raise it to the next power x3 cubed and divide by 3, x3 cubed over 3e IAB, evaluated at 0 and 9 meters. So we'll have 9 meters cubed over 3 EI minus 0. And that will equal 243 meters cubed over EI for member AB. And then let's evaluate that incorporating our quantities for modulus elasticity. So 200 gigapascals is also 200 times 10 to the 6th kilonewton per meter squared. Our moment of inertia is 1,250 millimeters to the 4th. And so we have meters to the 5th in the numerator. Let's convert that all to millimeters by multiplying by 1,000 millimeters per meter raised to the 5th power. Put that together, I get a positive 0.972. That's millimeters per kilonewton. And again, down is positive, just like it was for delta C. So that means if we go all the way back to our original compatibility equation, remember we drew our unit redundant up. And so the calculation we made in step 4 should have been a force applied up. We can correct for that, no problem. It just means that my flexibility coefficient is actually a negative 0.972 millimeters per kilonewton, because we originally drew it up for our compatibility equation. Now step 5. Let's find that redundant value. So our equation of compatibility was delta C plus Cy assumed up. Flexibility coefficient, if we calculated it for an upward deflection, add to 0. Delta C we found to be 27.2 millimeters. To which we add Cy, and if Cy is up, we said our flexibility coefficient was a negative 0.972 millimeters per kilonewton, and all of that adds to 0. Solve that for Cy, and we get a positive 28.0 kilonewtons, acting up. Now step 6. Let's find the remaining support reactions. We have an unknown vertical reaction AY, unknown horizontal reaction AX, unknown moment reaction MA, and Cy we now know to be a vertical reaction of 28 kilonewtons. Let's Let's apply horizontal equilibrium first. We'll take to the right as positive. We get AX minus the concentrated force, and AX must be 2 kilonewtons to the right, as drawn. Now let's sum forces in the vertical direction. We'll choose up for positive. We have AY minus the uniform distributed load, 8 kilonewtons per meter, acting over 9 meters. And then we have the 28 kilonewtons acting vertically at C. Put those together and we find AY as a positive 44 kilonewtons acting up. And we'll sum moments about point A. We'll choose clockwise as positive. We have the unknown moment reaction at A. We have the effect of the uniform distributed load, the resultant force we get when we multiply by 9 meters. Its distance from point A is 9 meters divided by 2. We also get a positive contribution from the concentrated force acting through 3 meters, and a negative contribution from the vertical reaction at C acting through 9 meters. Put all of these together, MA is a negative 78 kilonewton meters, and we drew it originally as clockwise. And to wrap up, we have step 7, where we compare with the approximation. If we go back and look, our AY approximate we said would be 36 kilonewtons, as well as CY. And we found AY to be 44 kilonewtons up and CY to be 28 kilonewtons up. So as we compare these, they seem reasonably close. Our approximation of the moment reaction at A we had found, or predicted to be approximately 81 kilonewtons, not in the clockwise direction. Kilonewton meters, that is. Not in the clockwise direction. And using the force method, we found it to be a minus 78 kilonewton meters, not in the clockwise direction. Those are also reasonably close. So by comparing with our approximation, we can be reasonably sure that our force method results are producing quality predictions of the reactions. Now let's go back and review the process we took. We started by generating an approximate answer so that we would have something to compare our force method results to in order to ascertain whether they are reasonable or not. And we simply said, let all of the uniform distributed load go to its nearest vertical support reaction. Then we said, what if we idealize this frame by ignoring member BC, ignoring the impact of the relatively small concentrated force on the moment reaction at A, and we used information from the back cover of our textbook in order to calculate the moment for an indeterminate beam fixed at one end, roller at the other, uniformly loaded. We then calculated the degree of indeterminacy, found that it was 1 degree indeterminate, so we needed 1 redundant. We chose the vertical reaction at C as the redundant and wrote the equation of compatibility for vertical deflection at C. In order to get the vertical deflection at C of the primary structure, or that is the structure without the redundant, we need to use virtual work. So we started by calculating the moment equations due to the virtual force and found that 2 of them are 0, which means we didn't need to determine or calculate the moment equations in region x1 or x2 due to the real loads. We then combined our moment due to the virtual load and the moment due to the real loads in the virtual work formula, found our deflection delta C, repeated the process for the deflection under the unit redundant. We drew it initially down, but our compatibility equation was based on a cy acting up, so we flipped the sign in our flexibility coefficient to denote an assumption of a upward reaction at C. We then use that information with the compatibility equation to find the redundant, the vertical reaction at C. We then used our 3 equations of equilibrium to find the remaining support reactions. Then we went back and compared with our approximate results, found that they were relatively close, and so we are reasonably sure that we have quality prediction of the reactions at A and C due to the uniform distributed load and the concentrated load for this indeterminate frame. Well done.